to you in class work. So this is a program that basically makes phase portraits, and here it is, and I just want to first run it, and then we can talk through how it works. So if you open the program, which is called makephaseportrait.m in your home directory, and then you just push this little green button, it will run, and you see what it does is it makes the phase portrait of the set of differential equations we talked in class. The fixed point is here at the origin. This is the unstable manifold, which points along the direction 1, 1, and this is the stable manifold, which points along the direction minus 4, 1, which you'll remember from class. And these are arrows showing the direction of the velocity field that the differential equation implies. So now let me just show you how the program works so you can use it for your homework. So the program starts here. So we start by just creating a new figure window. Then there's this command which looks odd. It does something which is called mesh grid. And what you see is that it returns two arrays, x and y, and basically what it does is it creates the mesh upon which these arrows are drawn. So if you look at this picture, you'll see that basically that the arrows, there are basically 20 arrows across and 20 arrows up and down. So here let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you see there are 10 on the top part of the positive part of the y-axis and 10 on the negative part. And these arrows are centered at the x coordinates, which go from minus 10 to 10, and from y coordinates, which go from minus 10 to 10. And that's what this command mesh grid does. So if I just go to the MATLAB window and I type x, then you will see that basically x is essentially a matrix which every row goes from minus 10 to 10, and there are 10 such rows. And if I do y, it's the same basic thing. So the points on the elements of x and y basically give the coordinates at which these arrows should be drawn. So then the arrows themselves are drawn by the command quiver. So x1 and y1 are the differential equations. So x1 is x prime, which is x plus y, and y1 is y prime, which is 4x minus 2y. That we've plotted here. And then quiver simply plots the arrow of magnitude, with direction x1, y1 at the point xy, and it plots the vector field everywhere. We then just label the plots. We put a title on the plot. We show the grid because the grid is sort of cool on this. You can see the background grid, and then that's that. And I just basically in order to compare it, I plotted the first eigenvector and the second eigenvector that we computed in class, namely 1, 1, and 1 minus 4, so that you can see them. Those are the red lines, so that's why it says plot. There's this quote red that colors it red. And then also, just for fun, I plotted a trajectory on top of this. So this black curve is a trajectory. We solve the differential equation starting with x equals 2 and y equals 8, and we then solve it. And basically this plots the trajectory. So you see this starts at 2, 8. You see how this starts at y equals 8, x equals 2, and then it proceeds as follows in time, which is what you would expect given the direction field. Notice that in order to plot the trajectory, I needed to plot the two columns of the vector y against each other, because what this differential equation, since this is a second order differential equation, what it actually returns, if we look at y, is two columns of numbers. The first column is the variable x, and the second column is the variable y. That's basically why I'm plotting the x coordinate of the solution against the y coordinate. And that's that.